Servo systems consist of a motor, controller, feedback device, and drive. The controller determines what torque, velocity, or position is needed from the motor and then triggers the drive to send the electrical energy necessary to let the motor move as commanded. No wonder servo drives are sometimes called amplifiers for how the controller's modestly powered control signal informs the shaping of far larger motor powering voltage and current. One common servo drive is the torque mode amplifier. These adapt the controller command signals into current to the motor with torque produced directly proportional to that current. That's because servo motor torque is equal to the cross product of current and the motor constant. Key to sizing a servo drive and motor is the torque speed curve. Often, this torque speed curve is specific to a certain motor drive combination. This is because a motor's continuous and peak torque capabilities are affected by the thermal properties of both the motor and the drive. Motor inefficiencies can cause heat production, which in turn can degrade bearing lubrication and insulation around the motor windings. Excessive heat can even damage the drive electronics and, where applicable, demagnetize the motor's magnets. Problems causing excessive heat generation abound, but operating a servo design at peak torque, peak current, for too long is perhaps most detrimental. Note that continuous torque is the torque the motor can indefinitely produce. On a torque speed curve, the continuous torque range is the basis for evaluating the RMS torque required by the application. Peak or intermittent torque is the maximum amount of torque the motor can produce for a short amount of time without overheating. Running a motor at its peak torque value is typically only allowable for a few hundred milliseconds. So in contrast with traditional continuous duty solutions, some servo drive motor combinations designed for rapid acceleration and deceleration, in other words, high peak torque needs, are sold as pulse duty components. Pulse duty servo drives have a high current overload rating and pair with pulse duty motors having lower inertia than conventional designs to reduce the amount of torque, and thus current, required for demanding move profiles. Continuous duty drives, in contrast, prompt higher torques at higher speeds on a continuous basis with only moderate peak torque capabilities. Servo drives were originally standalone components separate from the motor and controller. But in the past 20 or so years, numerous motor manufacturers have developed integrated drive controller offerings, as well as integrated motor drive systems, and even complete motor feedback drive controller systems. Slightly complicating matters is that these integrated designs, which include the motor, feedback, controller, and drive, are sometimes simply called drives for their axis driving function. They tend to reduce wiring, make sizing and selection easier, and save considerable space and setup. Even some servo drive offerings considered standalone components integrate digital positioning electronics for streamlined controller functionality. Some servo drives employing digital technologies work with DC brushless, PMDC brush, and stepper motors to simplify the design of high-volume OEM product lines that may use different motor types. Still, other servo drives can work in both AC and DC servo motor applications. Full tuning of a servo system includes servo drive accommodation. Multiple control loops, each with its own gains and proportional, integral, and derivative parameters, require adjustment. And tuning a servo drive usually requires adjustments to parameters including acceleration and velocity feed-forward gains, as well as filters to reduce oscillations. For more videos like this, visit designworldonline.com/videos.